Hi, my name is Ramon Gomes da Silva. I am a PhD student at Pontifical Catholic University of Paraná, and I'm going to present you the paper entitled Prediction of Residential Buildings Efficiency based on on differential evolution optimization in random forest model. The agenda of the presentation is going to be the introduction, the dataset, the methodology, the results, and the conclusion. So, in Brazilian context, residential buildings demanding 51% of the produced energy. The prediction of heating and cooling loads of residential buildings plays a key role. Once the heating, ventilation, and air conditioning systems are drivers of the energy demand. So associates feature engineering, feature selection, and ensemble learning models allows to develop an accurate predictive system. So the objective of this paper is to evaluate the predictive performance of the predictive systems by combining FE, FS, and ensemble learning models. In the FE stage, statistical features are computed based on the inputs of the system. In the next, to obtain the most suitable set for features, two approaches are considered. The first combines DE optimization and random forest model. The second combining PCA and random forest model. So in this paper, there are two main contributions. The first one is to compare the different approaches to perform feature selection, the differential evolution algorithm, and dimensional reduction, the PCA. The second contribution lies in the development of an integrated framework which employs feature engineering, feature selection, and ensemble learning models to predict heating and cooling loads of residential buildings. So the dataset adopted in this paper was proposed by Tissanas and Schifara, 2012. 12 different building shapes were taking the elementary cube simulated in ECOTECT. There are 2 inputs, Y's, and 8 inputs, X. So there are in the table 1 the description for each one of the inputs and the outputs. So the both outputs are heating load and cooling load, and the inputs are relative compactness, surface area, all area, roof area, overall height, orientation, and glaze area, and at the end glaze area distribution. So we're gonna call them x1, x2 until x8 for each input. So the phi is used to obtain the statistical features based on the inputs of the systems, and the random forest is combined with the DA algorithm for feature selection, and the random forest is combined with the PCA. So at the end, the mean square error is computed. So it is well known that feature engineering is the core of the data modeling. So the feature engineering is the task of formulating the most appropriate features given the data, the model, and the task. So in this paper, for the inputs features presented in the table before, 33 features are obtained according to 2 strategies. The first strategy consists in computing the exponential of order 2 and 3, hyperbolic tangent, and logarithm for features x1 to x8. In the second strategy, for the respective output for the set of features are computed the average, median, standard deviation, minimum, maximum, and skewness. After performance, the feature engineering, For each variable response, there are 41 features. So the feature selection is the process designed to solve the trade-off between finding the smallest subset of features, which with the best classification accuracy, and the use of the optimization algorithms. Performing feature selection has been explored extensively in the recent years. Therefore, in this paper, the wrapper approach, which combines the random forest model with the differential evolution algorithm, is employed. By combining random forest and DE, the optimization process starts generation an n-size vector, which n is the total number of features in a dataset, and each position of the vectors can only assume values such as 0 and 1, where 0 represents the features that are not selected and 1 represents the feature that were selected. According to the selected features, the random forest is trained using 10-fold cross-validation, and the cost function is computed the MSE, the mean square error. So the process is conducted until the optimization process ends. Thus, the set of the selected variables, those with higher values than 0.5, is obtained. On the other hand, a second approach which can be employed to filter the computed features, and in this case, for feature dimensionality reduction, is the PCA. The PCA is the technique widely employed for dimensional reduction or feature extraction coupled with machine learning models. In order to compute the accuracy, 10-fold cross-validation is employed. For each variable and each approach, the random forest coupled with DA or PCA is performed by 30 independent runs. In the end of the process, the mean square error and feature importance are computed. Well, there are the results. Consider the heating load. The best predictive model is the DE random forest, which use DE for feature selection and random forest for predict the output variable. In the terms of average accuracy of the 30 independent runs, this approach is able to enhance the accuracy, where the improvement in the performance is 61% and 11% regarding PCA random forest and random forest respectively. On the other hand, for cooling load variable, the same results are achieved, where again DE random forest provide better accuracy in terms of MSE regarding to compared models. In fact, the improvement in the performance is 9.72% and 11.63% regarding the PCA random forest and random forest respectively. So both figures 2 and figures 3, illustrate the scaled feature importance of each feature selected by the DE algorithm and used by random forest ensemble learning model to predict the heating load and cooling load respectively. Considering the computed features for both cases, the feature based on glazing area X7 has high importance compared with the remaining features, especially exponential or order 2 and 3 for heating and cooling loads. Also, the hyperbolic, tangent, and median features are important to predict heating and cooling load respectively. Considering the original data features X1 to X8 for heating load, the most important features are is relative compactness X1, overall height X5, and glazing area distribution X8. Moreover, to predict the cooling load, roof area X4 and glazing area distribution are the most influential. Here then the feature importance for cooling load, and figure 2 is the feature importance for heating load. So according to Friedman tests, there is statistical difference between the MSE for the three adopted approaches for cooling and heating loads variables. Figure 4 illustrates the comparisons between three approaches obtained through Niemeyer post hoc tests. In this representation, those models that are not joined by a line can be regarded as different. Moreover, this information corroborates with the results pointed out in the table 2. The observed versus predicting heating load and cooling load, right and left respectively, are displayed in figure 5. While for heating load output, the proposed performance, the proposed framework, which combines feature engineering, feature selection, and ensemble and more, can capture the data variability. And for the cooling load, this model has some difficulties. So as a conclusion, an ensemble model was evaluated to predict cooling load and heating load of residential buildings. The GE random forest model outperformed the PCA random forest and random forest models in terms of MSE. As feature research is suggested to integrate stack ensemble learning and other optimization algorithms to predict cooling and heating loads in residential buildings. So we'd like to thank CAPES, CNPq, Fundação Araucária, and PUC-PR for financial this work. Thank you. If you have any question, give the comments below. Thank you already.